Okay, good morning, everyone. Dr. Nat here. We are doing module number 5, which is on random variables and also probability distribution. We already covered some of these this topic. And we discovered that we have two types of random variables, discrete and continuous. I'm not going to go over it again. And then we found out that we did some exercises up to this point. I'm going to go over this one a little bit more. So here we have, did we do this one? We did. Okay, let's do exercise number 3. Suppose that a day's production, 850 manufactured parts, contains 50 parts that do not conform to the customer requirements. I know we've done this before. Let me just go over it really quickly. 2 parts are selected at random without replacement, meaning to say when you take out one, you are left with 849. This is what it means when without replacement. And usually when you do probability problems, a lot of them do not replace the items that you take out. So this is fairly common. From the batch, let the random variable x equal the number of non-conforming parts, which means that it has a defect or it is defective in the sample. What is the cumulative distribution function? Okay, so we did this one and the answer was this. If my defect is 0 from the 2 samples that I choose, both of them are non-defective or they are conforming to the specs that I want. Therefore, my x is equal to 0. Okay, so x denotes the defect of how many defective items that I choose. So if both of them are not defective, therefore x is equal to 0. If I choose out of the 2 that I choose, one of them is defective, therefore x is equal to 1. And if I choose 2, both of them are defective, therefore your x is equal to 2. Okay, so remember that we have 50 over 800 parts that do not conform, meaning to say that they are defective. Okay, I'm going to get you guys up to speed. 50 over 850 is defective, and non-defective, meaning to say it's good ones, would be 800, right? And my face is over here. I need to put it somewhere else. 800 over 850. If I take one out of the non-defective items, therefore the non-defective items that is left will be 799. If I take one out of the defective pool, therefore my defective will be left 49 over 850. So every time you take one out of the pool, you have to subtract one. Okay. So Px equals to 1, probability of random variable x is equal to 0 is 800 over 850. And then when you take one out of the non-defective, you are left with 799 over 849. So this is the probability that both of the items that you choose is non-defective. And then if you have, if you choose one defective item and the other non-defective, the way that you can go about this one is you choose a defective item with a non-defective item, or you choose a non-defective item with a defective item. So you have two outcomes for this pair, right? So 2 times 800 over 850 times with 50 over 849. And then if you choose both of them to be defective, therefore it will be 50 over 850 times with 49 over 849. So we did this one already. So we want to find out what is the cumulative distribution function. Now, what is cumulative distribution function? It is actually the number that when your variable is equal to a certain number and the number before that. For example, your f in bracket 0 means that your probability that x is equal to 0 or anything before that. And then if you have f, capital F, in bracket number 1, it means that probability that random variable x is equal to 1 and less or before that, right? And then also the same case, f in bracket 2 is equal to the probability that random variable x is equal to 2 or less than 2 or anything before that. So here we know that when x is equal to 0, it is 0.886, right? So 0.886 is 0. So this is my x-axis. Look at the graph over here. This is my x-axis, and this is my y-axis. My y-axis will tell me my cumulative distribution function, or like the values, right? And x is the random variable. To make this bigger because it's quite small. Okay, so your x-axis is your random variable. It can be x, can be y, it can be z. Doesn't matter as long as it is a random variable. And your y-axis will be the probability, right? The cumulative distribution function. Okay, so we know that when p probability of x equal to 0 is 0.886. So how do we plot this? So at 0, I put in 0.886. We just put a dot there first. And then for probability x is equal to 1, it is 0.11. But we want to know what is the cumulative distribution function. Therefore, we need to add up anything that is equal to 1 or less than 1. So what is equal to 1 and less than 1? It is these two probabilities. So we add this 0.886 plus 0.111. So we get 0.997, right? So for number 1, it is 0.997. I just put a dot there to plot it. That's it for now. And then the next one is cumulative distribution function of 2, which means that the probability of x equals to 2 or less than 2, which means that it is equal to 2, and anything that is less than 2, which means it's everything over here. So you have to add all of this probability to get your F2, right? So 0.886, 0.111, and 0.003 will give you 1. If this is a real probability mass function, or a real probability density function, oh my god, this is a mouthful, then it will always be equal to 1. It means that it is complete. If it is not complete, meaning to say you add them all up and it does not equal to 1, then it is not a valid probability density function or probability mass function. So the way to verify if this is a valid probability mass function is to find out if everything is equal to 1. So that's a potential question, okay? Finding out if it is a real probability mass function. Okay, continuing with that. So cumulative distribution function of 2 is equal to 1. So I'm going to put here 1. Okay, so please observe here, the dots that I put here is blacked out. And this one is hollow. Okay, it's hollow. The place that you put in the hollow dots is where it has the jump. Okay, when you have discrete functions or discrete sample, you would have probability mass function, right? And it is not continuous. So this is why you have that jump. It's not going to be continuous. There is a gap. Remember our discrete sample, there is a gap between the numbers. The graph also has that jump, or it also has that gap. Okay, so again, we have our values over here, and anything that is beyond 2 will obviously be just 1, right? And anything that is less than 0, it's not supposed to be blacked out. It is hollow. Anything that is less than 0 should be, whoops. It's just, you just put this arrow like this, okay? But there's no value there. It's a hollow circle, it's a jump. So at 0, it is 0.886. At 1, it is 0.997. And at 2, it is 1. So you just extend your lines. Extend your dots over there. Okay, so something very important to take note, you have your values here, the actual values, and the hollow is your jump from one value to another. It's not continuous. This is why you have that jump. And since it is a cumulative distribution function, it has to have some value. You can't say, oh, at this point, there's nothing happening. No, because it is cumulative. It takes up into account all the values that you already have. Okay, so this is how you plot it. Any questions? So this is your recap for today. Okay, continuing. If you have any questions, please just interrupt me as usual. Okay, so we're going to continue with continuous random variables. I talked about a little bit on continuous random variable, and I told you for discrete sample space or for discrete random variables, you call it probability mass function. For continuous random variable, you call it as probability density function. Density. Probability density function. So that's the difference. There are two names here, one for continuous and one for discrete. And sometimes the general name for them, for both of them, the discrete and the continuous random variables, you can just call them as probability distribution, but you won't know whether the sample space is discrete or continuous. That's the general name for it. Okay, so if our discrete sample space has gaps in our graph for the continuous random variable, you won't have that gap. It's all a continuous curve. Okay, so looking like this one. Okay, so it doesn't really have to be like a bell curve. It doesn't have to be symmetrical. It doesn't have to be skewed. It can be, actually, it can be like this. It can look really funky, like can start from here to here. As long as it is a curve, it can count for a probability density function. Okay, so just keep that in mind. Okay, moving on. So what is continuous probability distribution? Let X, which is a random variable, be a continuous random variable with probability density function. Now, for our discrete, our probability mass function was a small p with X. You have to differentiate it between probability. Probability is capital P with X is equal to something value. This is probability mass function, and continuous probability distribution is small f X. Okay, let A and B be two numbers where A is less than B. Therefore, then the probability of your random variable X equal to A or greater than A or equal to B or less than B is also equal to the probability of your random variable X is equal or greater than A or less than B, or it is also equal to probability of random variable X is greater than A or less than or equal to B. What it's trying to say here is that these things, whether it's equal or not, doesn't really matter. It's the same. You don't have to have that equal sign. You don't have to have this guy. It's not important. It just means the same thing as if it is less than or greater than. Okay, so it is also equal to this guy. So it's just all the same. We are a family, whatever that means. Okay, so this is going to be equal to the integration of function fx with respect to dx, with respect to x, from a to b. The integration of the function x with respect to x from a to b. Okay, so in addition, your probability where x is less than or equal to b will also be equal to the probability of random variable x less than b. I told you before, it's just the same. It doesn't matter if it has that equal sign or not. Okay, and if we're talking about the probability of random variable x less than b, therefore we can imagine it like this. Okay, we're talking about the probability of x being less than b, right? So let's say a is less than b. I'm going to put a over here and I'm going to put b over here. So my curve is from A to B, let's say. So if I wanted to know what is the probability that X is less than B, therefore anything that is before B up to B is what I want to find out, right? So it extends from minus infinity up to B. So this is what it's trying to say. And if my probability of random variable X is greater than A, it means that I am finding the, I'm integrating from A up to infinity. I'm integrating from a up to infinity. Let's see, let's use a different color. From a up to infinity, which covers this part. So the part that they overlap is just over here, right? So when I am finding something that is less than b and also greater than a, it only covers under the curve. Okay, so this is what it means. When I'm integrating between a to b, I'm only integrating under the curve, only the part that it overlaps. Okay, only the part that it overlaps. Yeah. Okay, so this is just like the theory of it. This is the probability that the random variable x takes on a value between a and b under the probability density function. The area under the curve does not depend on whether the endpoints a and b are included in the interval. Like I mentioned to you before, doesn't matter if it's equal or not, it's still going to be integrated together. The area under the entire curve is always equal to 1, just like our probability mass function. The sum of our probability mass function is equal to 1. Same case over here. The sum of when you integrate the entire curve, it will be always equal to 1. From minus infinity up to infinity. Okay, so this is an example. Any questions, please interrupt me. Okay, so a hole is drilled in a sheet metal component. Okay, so we have a sheet and we are drilling a hole. Okay, just trying to visualize that for you. And then a shaft is inserted through a hole. So if you've done your homework or your assignment or your activity in class for AutoCAD, you would know what a shaft is. It's something like really long with some endpoints, don't know. It looks like whatever that you drew in your AutoCAD class. Okay, so you put in a shaft inside that hole that you just drilled. The shaft clearance is equal to the difference between the radius of the hole and the radius of the shaft. What does that mean? You're putting in the shaft, okay, and whatever, so you have your radius of the hole, right? This is R1 and this is the radius or the diameter of your shaft, R2. So the difference of the radius of the hole with the radius of the shaft is the shaft clearance. This is your shaft clearance, okay? So whatever that is left, whatever the gap is, let's just say that, okay? The gap is your shaft clearance. Let the random variable x denote the clearance or the gap, right? In millimeters. So the probability density function of x is, so here you have your fx, because it is a continuous probability density function. And it gives you 1.25 times with 1 minus x to the power of 4. If your random variable x is between 0 and 1. Otherwise, meaning to say if it is before 0 or less than 0 or greater than 1, it will become 0. There's no gap. This is what it means for this function. Okay, so question. Components with clearances larger than 0.8 millimeter must be tossed out. Okay, must be tossed out, meaning to say we don't want it. And what is the proportion of the components that gets tossed out? So we want to know what is the probability of x being greater than 0.88. 0.88, sorry, the probability of x equal to 0.88. Sorry, it's just larger than. So there's no equal. So we want to know what is x greater than 0.8. So this is what we're trying to find out. Excuse me. Okay, so let's see. So if we were to plot this function of 1.25 times with whatever this is, assuming that we know how it looks like, this is what we're going to plot. And we only want to know what is this portion of the curve. Our curve is from 0 to 1. Otherwise, it's just 0, right? So beyond 1 is 0. Less than 0 is also 0. So the function only exists between 0 to 1. So this is what it means over here. And when we're trying to find what is the probability of the x being larger than 0.88, you actually have to integrate this entire section. And as you can see over here, the 0.8 is included in the integration because for continuous probability distribution, the endpoints are always included whether or not you want to include it or not, because it's going to be there. You have to integrate it. So it's just the same as probability greater or equal to 0.8. It's the same with this guy. This is what you're getting. Okay, so if we want to know what is the probability of x being greater than 0.8, therefore you have to integrate the function from 0.8 up to infinity, because you're going to be going greater than, right? So you put in your function 1.25 times whatever that is. This is a constant. If I were to do this myself, I would put out the constant over here, okay? And I have my function 1 minus x to the power of 4 over here inside, and my dx. I'm assuming in semester 1 you already did integration. Is that right?
Yes, doctor.
Okay, that's good. I don't want to teach you integration. That's a whole different topic. Okay, so 1.25 times with 1 minus x to the 4, and you're going from 0.8 up to here. I put it as infinity, but you know that your curve only extends up to 1. So you start with 0 up to infinity, and then you replace your infinity with 1. The same case if you put it from minus infinity to 0.8, let's say, you are integrating this section. So what you do is you put in this value first, and then as you progress along your working steps, you put in the actual value, which is just 0 to 0.8. Okay, so you can't have your infinity over here. You have to replace it with some value. Okay, so assuming this is what we have, so I integrate 1 minus x to the power of 4. So now it becomes x minus x to the 5 over 5. And my constant is over here, meaning to say I have to multiply this with whatever that is inside my bracket. And the value that I should integrate this, or I have to put in the values from 0.8 to 1. Okay, so 0.8, you can do the math yourself. Afterwards, you can multiply it with 1.25. You would get 0.0819. So this is what the portion is, 0.0819, which makes sense because the entire curve is 1. If you're only going to integrate a small portion of this, it should be a small number, right? So this looks right. Okay. Okay. So any questions about this one? Fairly straightforward, right? Just integrating. So other types of density function, other curves, it can look like this, or a straight line, or a symmetrical bell curve, or something like this. And you have to, when they ask you to find out what is the probability between some value A up to some value B, you are just integrating the area between A and B. Okay. So if probability of random variable x is greater than A or less than B, this is the area that you are finding. And you have to put in the function like this. Okay. So we talked about continuous probability distribution. Now we have to go into cumulative distribution function, because why not? So cumulative distribution function of a continuous random variable specifies the probability that a random variable is less than or equal to a given value. So it is the same exact definition as our discrete random variable. It is the probability that a random variable is equal to or less than a given value. Whatever that comes before it is part of the probability. The cumulative distribution function of a continuous random variable x is just as it is for a discrete random variable, whereby you have your capital F here. It is equal to the probability that x is equal to or less than some value. Okay, so this is the definition. So basically what you're integrating is anything from minus infinity up to x. But remember, our function has some how do I say this? Our function only exists from a certain number, right? So if you know what your a and b is, or you know that your function is from 0 to 1, therefore your minus infinity will be 0. Any questions? I'm going a little bit fast because we only have 1 hour and we have a lot to cover before our test. And I also have to make up for yesterday's class. So have a look out for that one. I'll give you guys a recording. Okay, so cumulative distribution function of a continuous random variable. Let's say this is our function, the same function that we had before. Since ft is defined separately on 3 different intervals, the computation of the cumulative distribution function involves 3 separate cases. Okay, so let me say that again. Since our function is defined separately on 3 different intervals, so here we only have 2. So what 3 intervals are they talking about? Remember when we had our curve, right? Let's say this is A and this is B. This is where our function exists. And anything beyond it is a 0. Anything below it is also a 0. So this counts as for one interval. This counts as for another interval. And this counts for another interval. This applies for any curve. Okay, you have to have that interval before and after the function exists as well. So let's say, let's do our 3 cases here. If x is less than 0, therefore you have to integrate from minus infinity up to x. So minus infinity up to x is just 0 because it doesn't exist before 0, right? And if your x is from 0 to 1, our function exists. So we put in our function. So here we are putting minus infinity to 0, sorry, minus infinity up to x, but here our x is from 0 to 1. Okay, so I have to include this guy over here in my boundary, okay? So minus infinity is 0, I integrate the function, plus with 0 up to x. I'm not including 1, because this is cumulative function distribution, meaning to say I only want whatever that is before the number, right? So I am taking into account that the boundary is from 0, but I don't want to put in the 1 yet. So this is what I have, minus infinity to 0 and 0 to x. Bear with me, I know it's a little bit confusing. And if it is from minus infinity to 0, it's just the same as this guy, which is 0. And if it is from 0 to x, your function exists, right? So you put in your function and you integrate whatever you have over here. Okay, so you integrate from 0 to x. What you do is you integrate like normal, and then you put in your x inside your x is your value. Okay, so you would get 1.25 x minus x to the 5 over 5. And then your third case, if x is greater than 1, now you put in the 1 here. So you put in minus infinity up to x, because this is just our standard definition for cumulative distribution function. You have to have this. And then you put in the actual values for your boundary. So it goes from minus infinity to 0, 0 to 1, and 1 to x. You have to have that x. Okay, look closely. So it's minus infinity to 0, 0 to 1, and 1 to x. You have to have that x either way for any cases. Okay, so you know this is 0. We already did this one. And 0 to 1 is just this guy over here. And from 1 to x, it is 0 because our function does not exist beyond 1. So it's just plus with 0. So if you integrate this with respect to the boundary 0 and 1, sorry, with boundary 0 to 1, when you put in the values here, you will get 1 because this is a complete probability distribution function. Therefore, you will get 1 as your total probability. Okay, so I know it's a little bit confusing. It takes a while to understand this. We're going to do some exercises. Okay, so note that cumulative distribution function in example, the previous example that we did, is a continuous function. There's no jumps in the graph. Okay, there's no jumps in the graph. Remember for our cumulative probability mass function, we had something that looks like this. Hollow, hollow, and this guy like this, right? Have black dots over here. So this is our cumulative distribution function for discrete sample space. And this is how it looks like for a continuous sample space or continuous random variable. There's no jump, there's no gaps. Make sure you take note of the difference in the graph, okay? Because you have to plot it. Okay, so now we have 3 intervals, which means that we do have something of 3 intervals, right? So when x is equal to or less than 0, it is 0. When x is between 0 and 1, it is this function. And when x is greater than 1, it is just equal to 1 because this is cumulative, right? We're just taking what we got over here. Okay, 0, 1.25, whatever this is, and 1. So this is our 3 intervals. And we put it like this. So if I ask you list out the cumulative distribution function of a continuous random variable, this is how you write it down. This is how you list it out. If I ask you to plot it, I'm going to give you guys an easy function to plot, but you have to make sure it is continuous and not like this guy over here. This is wrong. Okay, so again, the x-axis is your random variable, and this guy is your probability. Okay, exercise. To make sure everyone is on the same page, let's do some exercise. What time is it? Okay. Does anyone have any questions so far? No questions? Okay. Sorry, I'm going a little bit fast because we have to catch up. Okay, exercise number 4. Suppose that the error in the reaction temperature in degrees Celsius for a controlled laboratory experiment is a continuous, okay, recording. For a controlled laboratory experiment is a continuous random variable x, having the probability density function. This is our probability density function. X squared over 3 when my random variable x is between -1 to 2. Everywhere else, it is a 0. We have 3 intervals before our function exists and after our function exists. 3 intervals still. Okay, verify that the probability density function is correct. So what you have to do is find out if it is equal to 1. So we have to, this is what we're trying to find. The function over -infinity over infinity. And B is to find out what is the probability when our random variable is greater than 0 and less than 1. So it is inside this interval. So let's find out how to do that. So to verify that the probability density function is correct, you have to find out whether it is equal to 1 or not from -infinity to infinity. So your interval is from -1 to 2. You put in your function x2 over 3, x to the power of 2 over 3. When you integrate it, it becomes x to the power of 3 divided by 3. So you get 3 times 3, right? X to the power of 3 divided by 3 times with 3, you get 9. So x to the power of 3 over 9, put in the values 2 and -1. So you would get 8 over 9 plus 1 over 9, and this is equal to 1. So we verified that the probability density function is correct. If it is not equal to 1, then it is not correct. Next one is finding out the probability if your random variable x is greater than 0 or less than 1. So I purposely did not say less than or equal to 1 because it means the same thing for continuous random variable. Okay, so we want to find out from 0 to 1. Let's say this is our curve. This is how it looks like. Let's say it doesn't look like that. I'm just drawing it randomly here. our interval, our curve exists from -1. Okay, obviously, that is not a -1. Let me redraw that. Okay, so it exists from here to here. This is -1, and this is 2. Okay, a little bit weird looking curve. -1 to 2, and I want to find out what is the probability that the random variable x is between 0 and 1. So from here and 1, right? So this is 0 and 1, and I want to know what is the area under this curve that I highlighted over here, or I shaded. So same case over here, x to the power of 2 over 3. I will get x to the power of 3 over 9. Same way to integrate it, but I'm trying to find out with boundary from 0 to 1 only. Okay, so I would get 1 over 9 plus 0. So it's just 1 over 9. So the probability of my random variable x from 0 to 1 is just 1 over 9. If you get this equal to 1, obviously it's going to be wrong because this is not your entire interval. So this is another way of verifying that you're not doing something wrong, right? Okay, for the same density function that we saw earlier, which is this guy over here, find the capital Fx, or cumulative distribution function. Cumulative. Oh, sorry. This is, luckily I'm not teaching you guys spelling. Cumulative, okay, distribution function. And also find out what is the probability of x from 0 to 1. Previously, we already did this one, right? We are expecting the value to be 1 over 9, but we're trying to find out using a cumulative distribution function. So let's see how that goes. Okay, so again, let's look at the definition for cumulative distribution function. This is the definition. If you're trying to find out cumulative distribution function, this is what you start out with. You go from -infinity up to x and your function. So let's do that. Okay. Okay. This one, they skipped a few steps. If we are looking at the steps that we did earlier, you would go from -infinity up to x, right? So here they just said, oh, whatever, I'm just doing -infinity up to infinity. Okay, that works too because you're trying to find the cumulative. But mathematically, it's not the most accurate, but it gets the answer as well. So -infinity up to infinity, so they just want to integrate the function where it exists, right? So it goes from -1 up to x. Definition of cumulative distribution function is you have to have your lower boundary up to x. It's always that case. Lower boundary up to x. Lower boundary up to x. Okay, so your lower boundary is -1 up to x. You don't include the upper boundary. So -1 up to x, x squared over 3. Here they use t instead. It's the same case. So t squared over 3, you integrate this with respect to t. This is why you have the dt. So t squared over 3 is just x to the power of 3 over 9, or sorry, t to the power of 3 over 9. Saying t is much more harder than x. I don't know why. And you integrate this over -1 to x. Okay, so the reason why they use t instead of x is because you have your boundary as x. So they just want to differentiate it. Okay, so you have, now you put in your x inside your answer. So it becomes x to the power of 3 over 9, and you put in -1. So x over 3 to the power of x to the power of 3 over 9 plus with, sorry, minus with, this is -1, right? -1 to the power of 3 is just -1 over 9. So you get x to the power of 3 over 9 plus 1 over 9. Okay, so you just leave it like that. You can't add it. You can't add x with 1. So just leave it like that. Therefore, your 3 intervals, you still have the 3 intervals, even though you skipped a few steps. anything that is less than the lower boundary of your function over here is going to be 0. Anything that is greater than your upper boundary over here is equal to 1, because it is the total, right? And anything that is between your interval where your function exists, it is this guy. This is your cumulative distribution function. Okay, so I've seen students get confused between the small fx and the capital Fx. Your small fx is your probability density function. And this is your curve, your actual curve. This is your cumulative, meaning to say at the end of the day, you have to have a value 1 over here. For your probability density function, you don't have to have that 1 because it does not, you're not adding up probabilities together. Okay, this one, you are adding it up. You always have to have that 1 in your intervals. Okay, something to take note of. Okay, continuing. 15 minutes to go. Okay, so if anyone has any questions, please ask me. Make this class more engaging because I can't make it engaging if I'm going really fast. Okay, so the cumulative distribution function, the same function that we're talking about just now, is expressed graphically in figure below. They give you this function, they draw it for you, and it is actually this function, right? It is 0 if it is less than -1. It is this function if it is between -1 to 2. It is 1 if it is greater than 2. So here, if it is greater than 2, it is 1. If it is less than -1, it is 0. And your curve exists only between the interval. Okay. So this is how you plot it. You don't have to plot it. Usually it's given because it's quite complicated to plot the curve. Okay, so now they want us to find out what is probability of x from 0 to 1 using the cumulative distribution function. Now you already know that your capital Fx is 0 if it is less than 1, 1 if it is greater than or equal to 2, and it was, what was it? X to the 3 plus 1 over 9. It's 1 over 9. If it is between -1 and 2. So they're asking you find out what is from 0 to 1. So what you do is if you have this function already done, you just plug in the numbers. Okay, so f1 minus f0 will give you the answer as you're finding out the probability from 0 to 1. Okay, so if I put in this as 1, so 1 plus 1 over 9 minus with 0 plus 1 over 9. I'm just putting the numbers inside this function. So this is 2 over 9 plus minus 1 over 9. I get 1 over 9. It is the same answer that I got before if I were to use the probability density function to find out this value, same case. So this is another way to use your cumulative distribution function. Oh, sorry, this is another way to find out the probability using your cumulative distribution function. Okay, so I'm out of breath. I'm going to take a 2-minute break. So please read this question. I'm going to call out someone to help me do this. Okay, so we have around 10 minutes to go. So read this question carefully. I'm going to call out someone to help me. So no one has any questions, right? So I'm assuming everyone understands what I'm talking about. Okay. So 2 minutes from now would be 9:50. Okay. So anyone wants to volunteer before I call out someone? So no volunteers. Okay, can I have Ashrif to help me? Ashrif, are you there? Ashrif, are you there? So Ashrif is here, but not here. So how is that possible? Okay, can I have Irfan Aziz? Are you there?
Yes, doctor.
Okay, so can you help me find out cumulative distribution function for this function? So what would be the first thing to do? Not the answer, just the step. What would be the first thing to do?
Do we need to equate it with the one? I mean, the 5 over 8b equate it with equals to 1 first?
5 over 8b is equal to 1.
The
Okay.
question needs to find b.
Correct. The area under the entire curve would be equal to 1. That's another way to look at it. Okay. So, oops, sorry. That. So, thank you. Tadi saya panggil siapa? Of Irfan. Sorry. Irfan? Yes, Irfan Aziz. Okay. So, who would be the next lucky person? Muhammad Hakimi. How many intervals do we have? How many intervals do we have?
Two.
Sorry, for the cumulative distribution function, how many intervals? What was important? We had to find out what was before our function exists, what is after our function exists, and also the interval where our function exists. How many is that?
Three.
3. Okay. So what would be my 3 intervals? Can you tell me? What would be the y? Yeah, how would you write down the intervals? So your y is less than or what would you put here? You have y is equal to 2 over 5b, right? Over here, and less than 2b over here. This would be y greater than? Y would be greater than?
2 over 5b.
Greater than? Or are you talking about the less than?
2b.
Which one is it? Can you say this your sentence properly? You got it correct, but was it greater than or less than?
2 over 5b less than y.
2 over 5.
And 2b is greater than y.
2b is greater than 2b is greater than 2b is greater than y. 2b is greater than y. Okay, let me write that down first. 2b is greater than y. Y is less than 2 over 5b. Okay, so if 2b is less than 2b is greater than y, is it the same or not with y is less than 2b? Is it the same or different?
Different.
Different? Sure. Okay, let's try to visualize this. I have a curve. My curve exists from, let's say, 2/5b to 2b, right? So you're saying 2b is greater than y, mean to say y is less than 2b. So y has to be before 2b, right? And y is less than 2b is also this guy. So even though it's flipped, it's actually the same thing because 2b is greater than y. 2b is greater than y. Y is less than 2b. Y is less than 2b. It's the same, okay? Don't get confused with this one. Okay, so hopefully everyone got that part. So how do I fix this interval? It's not correct yet. So y less than 2/5b, yes. What should be down here? Anyone? This is my first interval, we got this one. Second interval, we got this one. I want to know our third interval, which is over here. What is it?
Y greater than 2b.
Y greater than 2b. Anything that is beyond our where our function exists. Y is greater than 2b. And it says here, it is 0 elsewhere. So we already know that our cumulative function will be 1 over here because it has to add up to 1 and it will start with 0. The only thing that we have to find out is over here, this middle interval. Okay, so this is how you start with your cumulative distribution function. Find out what your interval is, write down the 0 and the 1, that's the easiest one. And then you find out what is the middle part over here. Okay. So here we're trying to find out what is the cumulative distribution function if our from minus infinity up to x, right? Because this is what we're trying to find for our cumulative distribution function. But of course, they skipped it here. They just straight away find out what is the lower boundary up to x. Remember, our density function is always lower boundary up to x. So if you're trying to find out what is the function or the cumulative distribution function from 2/5b up to 2b, you always only include the lower boundary. Always include the lower boundary only, okay? 2b/5 up to y. In this case, it's y. Typically, we go for x, right? So if this is an x, 2b/5 x. You only include the lower boundary. I cannot emphasize this enough, okay? You only include the lower boundary for your cumulative distribution function. Why? Because I told you when our definition for the cumulative distribution function is from minus infinity to x, your minus infinity or your infinity has to be replaced. So you replace your minus infinity with the boundary. Okay. So your function is, what is it? Function is 5/8b. 5/8b. So we integrate 5/8b from 2b/5 up to y. So here we are integrating it with respect to t. With respect to t. So your b is actually a constant. It's not a variable. It's not a variable, okay? So 5t/8b, because you're integrating it with respect to t, you don't mess with the b. So 5t/8b, and then you plug in the numbers 2b/5 to y. This is your boundary. So you would get, substitute t with y, you would get 5y/8b minus with your y, your minus with 2b/5, right? So 5 2b/5/8b. Okay, so now we can cancel this out, make our life easy. So this one also cancels out, you're left with 1. So you have 5y, you have 2/8 here, not 1. I missed this one. So you only have 2/8 left, okay? 5y over 8b minus 2 over 8. This is your cumulative distribution function between the interval 2 over 5 up to 2b. So you put it here, the middle part that we were missing over here. Okay, so 5y over 8b. Now I know you guys are thrown off because the boundary has some letters in it, right? B or like A. Just consider it like a value. If it helps you, just replace it with 1. But it's hard to track number 1, right? So just leave it as B. But remember, the B is just a constant. It's just like any other number. You just leave it. Don't treat it like X or Y in this case, okay? So I know it's a little bit confusing because of the B. Okay, so to determine the probability that the winning bid is less than the preliminary bid estimate B, so it's telling us find out what is Y less than B. So any questions? We just plug in cumulative distribution function with B, assuming that B is a number here. Okay, so how would that look like? So it is 0 from here, so we don't want that. So 5y over 8b minus 1 over 4. My y is my variable, so this is what I'm substituting with b. Okay, so it becomes 5b over 8b minus 1 over 4. My b cancels out. 5 over 8. This is 2 over 8. 5 minus 2 is 3 over 8. So this is what I get. Okay? Yes? No questions? Shami ada question? Shami Hazim?
No, doctor, no, doctor.
Okay. Right. Oh, okay. So I'm already out of time. So if you have any questions, let me know. WhatsApp is fine as well. I have a recording for you later on because we have to make up for the class yesterday. So I'm going to let you guys know later on. Okay, so take care, everyone. Have a great rest of the day. Sorry, it was a little bit fast today. Stop recording. Bye.
Thank you, doctor.
Thank you, Doctor.
Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.